Are we good?
Yeah, we're good.
Thank you. We're going to go through a Jupyter notebook on Tuesday and go over the code. So it should be fun, and then that will be, and then we'll talk about your final project. So we'll do that next week. So today, we're going to go over the algorithms and we're going to go over the algorithms, but talk about it in sort of a Python framework and how we're going to write Python code to the Ising model. Okay, so that's what we're going to do. Today's all about Monte Carlo. And it's important to realize that Monte Carlo is very general. You can use it to solve many kinds of problems. We're going to use it to solve the Ising model, but there's no reason you can't use it for other applications as well. I think for you guys to learn it, it's better just to focus on the Ising model so we have a concrete goal. So we're going to focus on the Ising model. Okay, so here's our goal in Monte Carlo. It really boils down to two things. One, we want to compute averages. So we need a formula to compute averages. For example, we want to know the average magnetization. Remember that curve we drew over there last class? At the very end of class, we drew the magnetization versus beta, or temperature, and we said that's our goal. And then we put Pablo's data on the board against Kevin's data. Remember that? So that's our goal. And to get those points on the curve, we need the average. We need to take an average magnetization at each beta. So that's what you're going to do in your computer code. And so we need a way to generate an average. So here's our goal. We need to use a computer to construct what's called a Monte Carlo trajectory. Okay? Use a computer. Why do we need a computer? Because we're going to need a trajectory that's, 100,000 or 1 million times long. So you don't want to do it by hand, right? Use a computer to construct a Monte Carlo trajectory. For now, I'm just going to call it a sequence of system states. A sequence of system states, okay, that satisfy the distribution of our ensemble. And we'll talk about that. Okay, and so this is most of the work in Monte Carlo. Okay, most of the work in Monte Carlo is we need to figure out a way to construct a sequence of system states that satisfy the distribution of our ensemble. If we can do this, then we have a simple formula for an average. Okay, so then ensemble averages are then carried out as this formula. Okay, so I'm going to calculate some average. This could be a magnetization. I'm going to use a quantity G to denote that it's general. Okay, so we're going to have the average of something G. This could be, for example, magnetization. Okay, average M could be something you calculate, something you will calculate. I'm going to put a capital T on this average because it's going to depend on the Monte Carlo trajectory. And it's a really simple formula. We take 1 over T. I'll define what T is. We have a sum over little t equals 1 to capital T, the value of G at little t. Okay? So at the end of the day, this is our formula. This is your go-to formula to calculate an average. Let me define big T, little t, and so on. So T, capital T is the length of the sequence. Okay, length of sequence. It's going to depend how long you run your computer. It could be, like I said, 100,000. It could be 1 million. Little t is basically the t member in the sequence. It's a member of sequence, right? And so what the sum is doing is it's summing over all members of my Monte Carlo sequence of states. And then g of t is just the value of g. G of t is value of g for this tth member. Okay? So that's the formula you're going to use. If we know how to construct a sequence and you know how to compute g for these different members, then this is pretty trivial. You agree? So all the work comes in constructing this sequence. So, of course we can compute an average. The question doesn't mean anything, right? Can we connect it to thermodynamics? And so there's a special requirement such that the average we get from a Monte Carlo trajectory actually has meaning. It gives us the thermodynamic average from the ensemble. Okay, so what we want, let's go through this. One thing is the sequence should be long. Okay, so just some notes. Okay. So in principle, okay, we use MC for Monte Carlo, right, for the rest of the lecture. The Monte Carlo sequence should be long enough so that all quantum states of the system appear more than once, okay? So that all, if we're doing quantum mechanics, we have quantum states. Ising model, we have spin states. So it doesn't matter what you say. Let's just say quantum states. Quantum states of system appear many times, right? And this is similar to the framework when we were constructing an ensemble, right? When we were constructing the ensemble, you said, okay, you need an ensemble, and you need many, many, many copies of your system in the ensemble, so that this is true. And so this is kind of the same requirement. If this is true, we can two things. Note that G is a property of the system, okay? So since G is a property of the system, it's only going to depend on the quantum state nu. Okay, so this is note one, any property of the system only depends on quantum state. Okay, so if we're going to use nu to label the quantum states, right, then G equals G of nu, right? So G depends on nu, and so really to know what a G of t is, we need to know what quantum state the tth member of the sequence is. And then if we know the quantum state, we can get G, right? Does that make sense? Okay. And so also, this allows us to rewrite this sum. If we're summing over G, and we're summing over a bunch of different values of G, but G only depends on nu, we can rewrite this sum in terms of quantum states nu. So we can rewrite this sum from t equals 1 to capital T in terms of a sum over quantum states. I'm just going to say a sum over nu. We'll just use a general label nu, right? So this is a sum over Monte Carlo, the sequence, right? And this is a sum over quantum states. Okay? And these two sums aren't equal until we put n nu in here. And n nu is the number of members of the Monte Carlo sequence that are in quantum state nu, right? So this thing right here is the number of members of the Monte Carlo sequence or trajectory in quantum state nu. Okay, does that make sense? Okay, so then what we're going to do is we're going to transform this average. This is the formula that you're going to use in practice. The following transformation I'm going to use just to tell us how we need to generate the sequence. Okay, so what we're going to do is transform. Okay, this expression, average G of t, is 1 over t, sum over t equals 1 to t, g of little t. Okay. I already said that g only depends on nu, so I can switch this sum using this identity. So this equals 1 over t, sum over nu, n nu, the number of members of the Monte Carlo sequence in its quantum state, times g nu. Okay? This is just a constant. T is just the total length of the Monte Carlo sequence. So it's like I can bring this inside the sum. Okay, so if I bring this inside the sum, I have an n over t. That's we're going to call a probability. So I'm going to say this is equal to sum over nu p nu g nu. Okay, where p nu equals n nu over t, right? If this is the total length of my Monte Carlo sequence, and this is the number of members of the sequence in quantum state nu, it's a probability that any given member in my Monte Carlo sequence is in quantum state nu, right? Okay, so is a probability of observing state nu in my Monte Carlo trajectory. And I'm gonna, interchangeably use sequence, trajectory, okay, and Monte Carlo sequence / trajectory. This formula looks really, really similar to what we define as the ensemble average, right? In fact, it's the same thing. It's just for an ensemble average, we have the probability distribution of the ensemble. Here, this is a probability distribution of my Monte Carlo trajectory. And so the point is that if my probability distribution of my Monte Carlo trajectory is the same as the distribution of my ensemble, then this gives me the ensemble average, right? So the point here is this. So the main takeaway, okay, is the Monte Carlo average, MC, the MC average, which is this guy, average G of t, will correspond to something physical, to the ensemble average. We know the ensemble average is physical. We know the ensemble average gives us thermodynamics. As long as P nu, this probability observing the state nu in the Monte Carlo sequence is the same as the probability distribution of the ensemble. Okay, so that's the key point. So the point is you're going to run a Monte Carlo simulation. You're going to use this formula. If you've done this correctly, and the probability of your Monte Carlo trajectory is actually equal to that of the ensemble, then you get a right answer. If you don't, you get a wrong answer. Okay, so when someone does a Monte Carlo simulation, whether their answer is right or wrong depends on whether this is satisfied. And there's some famous examples in the literature where people have done this wrong and they get a wrong prediction, and there's been a battle for the most famous. Is anyone going to? So there's a professor at Berkeley, David Limmer. I shouldn't say this. He worked for David Chandler actually, right? And there was a heated discussion between them and a group at Princeton. They were talking about super cooled water. And they were making a prediction. Princeton was making a prediction. You can read it. There's like comments in the literature back and forth. It was like a 10-year thing, and it turns out Berkeley was wrong because it was a complicated simulation, and this condition wasn't satisfied in their code, and so they made an incorrect prediction. So you have to be careful, and so this is we have to be really careful. And it turns out that whether or not this is true depends on a condition called detailed balance. And so we'll talk about a condition called detailed balance. Sometimes it's relatively easy to check that detailed balance is satisfied. Sometimes it's pretty tricky, as in that other case. Okay, so this is the point. Everyone get the point? We're going to use this formula. We need to make sure this is true. We get a physical prediction. That's the point. Right, so then basically the name of the game, right? All the work boils down to constructing a Monte Carlo trajectory, and say with physical P nu. By physical, I just mean it obeys the ensemble distribution. Okay, so that's really all the work, is to construct this trajectory. Let me pause for a second. Do you think we can ever, and I might have hinted this, do you think we can ever achieve this requirement? Probably not. What about for a system what about if we have a system as simple as a 2D icing model? Suppose we have a 20 by 20 lattice. So we have 400 spins. Do you think we can achieve this? No, I'm saying that head shake. No is right. Let's just see why. So note that it is impossible. Note that there will always be many, many more quantum states than we could ever sample. Many, many more system states than we can sample with our trajectory. Okay, and so let's just think about an example of this. Suppose we have a 20 by 20 icing model. So 20 by 20 2D icing model. How many states of the system are there in a 20 by 20 icing model? Even now. So each spin can be either up or down, right? So there's 2 possible states for each spin. I have 400 spins. So it's like flipping a coin 400 times. So 2 to the 400, right? So there's 2 to the 400 possible states, right? So this is 400 spins. So there's a number of states equals 2 to the 400, right? That's greater than 10 to the 100. Okay. That's an enormous number, right? That's more than the number of atoms in the universe, right? And this is just a simple problem, right? 20 by 20 Ising model, we can't even come close to sampling the number of states. So we can't, this obviously will never be able to achieve because, suppose you're, who was patient between Kevin and Pablo? I forget. Pablo was patient. Suppose Pablo's patient, and he runs his computer for a day, right? And he just crunches on his laptop for a day, or buys some GPUs, and he runs on like 2 GPUs. Maybe Pablo can generate 1 billion members. So maybe T equals 1 billion of Pablo's patient. That's 10 to the 9th. We're nowhere close. So Pablo goes out and buys more GPUs, and maybe he gets 1 trillion, 10 to the 12th. I mean, we're nowhere close, right? And so is all hopeless? Is all lost? No, otherwise we wouldn't be here, right? And so what's the resolution? How do we possibly have hope that this is ever going to work? The point is that we're trying to compute an average, okay? And the point is that only a small fraction of the states actually contribute in a meaningful way to the average. Okay, so the resolution is this. Only a small fraction, and I'll show you what I mean, of the states contribute in a meaningful way to the average. Okay. And so out of these 10 to the 100 states, 10 to the, 97 of them are we can just forget about them. So then our challenge becomes, okay, how do we pick out the important states and we disregard the ones that we don't care about? And that comes to the idea of importance sampling. And so Monte Carlo is a technique where you have a distribution. And so importance sampling is a general problem in statistics, right? Where you have a distribution and you want to sample the important part of the distribution and ignore the rest. And so that's what Monte Carlo lets us do. So Monte Carlo is an example of importance sampling. It is a type of importance sampling. And this is in a statistics class, even though it's called statistical mechanics. So we're not going to go into the details here. If you take a statistics class, you can go into the details. But let me just draw a picture for what I mean. One of our favorite distributions in this class is P of E. Okay, so example, what I mean by importance sampling of importance sampling okay, so let's look at P of, suppose we want to calculate average E from P of E for 2D Ising model. Okay. So that's basically, we're putting the energy in here. We want the average energy, right? And so we need the distribution of the energies, which is given by P of E. We're in the canonical ensemble, we're fixing the temperature, right? So we've seen what P of E looks like many times. So who can tell me what P of E looks like? Delta function, right? If there's one thing you leave this class with, it's that probability of energy is a delta function. Right, it looks like this. Here's E, And let me just, you have exponential decay, and you have exponential increase, this is the degeneracy, right? And P of E looks like this, right? Something like that. It's a delta function centered on average E. So let me put an E over here. Here's its center. It's centered on its average value. And it's a PV. Okay. Most of these, okay, I said there are 10 to the 100 states in the 10 to the 100 states in the 2D Ising model. Where are most of those states? They're on the sides. Actually, most of them are to the right? Because if you look at the degeneracy is telling you the number of states. And so there's a few states here. There's an enormous number of states over here. Right? So most of my states are over here, but my average is over here, so I don't care. Right? So most of my states over here. Most of my 10 to the 100 states. Right? Or in, I don't know, this region. So forget about them. We don't care, right? They're not going to contribute to the average because their energy is too high. Because the exponential decay kills them off, right? There's a lot of states, but the exponential decay, e to the minus beta e, kills off their contribution. Does that make sense? That's an important point. So we don't care. And so what our goal is in Monte Carlo, we have 10 to the 100 states. We throw out a huge chunk of them. Maybe Pablo's patient and he can pick out 1 million. He can run his Monte Carlo for 1 million t. T equals 1 million or 1 billion or whatever. So we're going to have 1 billion points here. And so maybe our Monte Carlo is a stick graph, which looks like this. Right? Something like that. Right? And so the goal is that this blue is going to be our Monte Carlo. So blue is basically the sampling in Monte Carlo trajectory T. Okay, does that make sense? And of course, if you compute an average from blue, it's going to look pretty good, right? Everyone get that? Blue is not the same probability distribution, but you've done importance sampling. You've sampled the distribution where it matters at the delta function. So when you plug in your formula to get the average, your average looks really close to the actual average. Okay, so this is really, really the heart of Monte Carlo. You're throwing out a huge chunk because they don't matter, and you're doing importance sampling to hit the important part of the distribution. Does that make sense? Questions, comments? That's pretty cool, right? If we can do it right.
If we can do it.
If we can do it right.
Because if you choose a random value, it's not going to be close to that, right?
Yeah.
So what?
You have to devise intelligent Monte Carlo algorithms.
Sounds like you have to know about what the average energy is before you.
You have to have some insight. You have to understand the physics of your system. For the Ising model, it turns out it's not too hard. If you want to devise a Monte Carlo scheme that could sample liquid water, good luck. It's hard, okay? Because then you would have to move the molecules in just a way so that they don't go to this right side of the distribution. Okay, so the whole challenge in Monte Carlo is devising these importance samplings. And so a lot of work. Basically all the research in there's still a lot of research on Monte Carlo methods applying to more complex problems. And pretty much all the research is focused on how to do this importance sampling well for different types of problems. That's where the research is. Okay, yeah, good comments. So that's the ansatz really. And there are different ways to do this. We're going to focus on the most common way. Okay, and the most common way is called Metropolis Monte Carlo. And so if you read the literature and you're reading about a Monte Carlo method, it may be Metropolis Monte Carlo, it may be different. I'll point out, we'll focus on Metropolis Monte Carlo, and then I'll point out where you change it to get different techniques. Okay, so here's our method. This is a method posed by Metropolis for how you're going to do this importance sampling. Okay, so Metropolis Monte Carlo. Okay, so this is one way to do the importance sampling. You know, it's one way to do importance sampling. Not the only way. It may be the best, it may not be the best. It's the most common way because it's simple. Okay, so I would say most common, and it's the most simple. So it's always a good idea to start with the simplest thing, unless you can justify going to something more complicated, right? So that's why we start with this. So I'm going to illustrate Metropolis Monte Carlo in the context of the 2D Ising model. Okay. So let's consider the 2D Ising model. And in the context of generating a Monte Carlo trajectory for the 2D Ising model, I'm going to define the important quantities that are general to any Metropolis Monte Carlo. Right? And so what our trajectory is really, it's a sequence of different spin configurations of the system. Okay? We need to generate a trajectory of spin configurations of the system. Okay? So the way we're going to do this is we're going to pick an initial state of my system, and then we're going to do Monte Carlo moves to make new states from the initial state. Okay? And so the workflow is step one, we choose an initial state. Okay? That's the first thing we do. And then we do Monte Carlo moves. Okay? So we have to do something to the system. We call that a Monte Carlo move. And from the initial state, we get more states in trajectory. Okay? So that's all we really do. We pick an initial state. We define a move. The move that we define has to obey certain properties for this condition to hold. Right? And if we've done our move right, we get more states in the trajectory, and when we do this over and over and over again on a computer, we've generated a trajectory that satisfies this. Okay, so the Monte Carlo moves, the key point here is these must obey a property we call detailed balance, which we'll define. Okay? So this is always how you do Monte Carlo, but then whenever you propose a move, you need to check carefully that your move obeys detailed balance. And we'll go over that. Okay, so let's go through this step by step. Let's start with initial configuration. Okay, and so you're gonna choose this on your computer. The easiest thing to do on your computer is probably either put all your spins up, put all your spins down, or make them all random. Right, so those are the different initial configurations you're gonna test. So let me just draw a small Ising model. So let's just say we have up, down, up, up, down, down, up, down, and then up, 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 down. Okay? And then more spins over here, more spins down here. Okay. I told you I was going to switch notation. Before we used one index to denote a spin, right? We said that a spin was denoted by I or J. But then I told you when we're writing computer code, it's easier to use two indices, one for the row, one for the column. So now we're going to switch to two indices to label our spin. And we're going to change n. N no longer is going to be the number of spins. It's going to be the size of the row and the size of the column. Okay? Just redefining variables. And so this is going to go from, column 1 to ... n. So we're going to have n columns. And we're going to go 1, 2, 3, ... n rows, right? Just like we're using 20 by 20 to describe our icing model instead of 400 spins. So we have an n by n system. And so we're going to label each spin. Each spin is labeled by index of row column. Okay, and so we're going to use the notation, in my lecture I picked IX for the row, IY for the column. You can use whatever, right? So we're going to label it. I just have I underscore X, I underscore Y for the row column. That labels my spin. Okay, does the initial configuration matter? Will the result depend on the initial configuration? I hope not, right? Because if it does, then you're all going to get different results. All right, and the analogy is, it doesn't matter how you prepare a glass of water. Once it reaches equilibrium, water is water. And so that's the point. The initial configuration shouldn't matter once I reach equilibrium. And you're going to test this. So you're going to show that the initial configuration doesn't matter. That choice of initial configuration doesn't matter. And so the way you do this is just choose a bunch of different ones, right? You'll choose all spins up, all spins down, all spins random, and you'll get the same answer. Okay, so here's what we're going to do. We've done step 1. Now we have to define a Monte Carlo move. Okay, so let's define a Monte Carlo move. What should we do? What should our move be? We need to change the system somehow. We could flip 1 spin. We could flip 2 spins, 5 spins. We could flip all the spins. Anyone have a preference?
Flip all the spins. That makes so much sense. Yeah.
So back to my when you're deciding what you're gonna do, probably the best bet is to do the simplest thing possible unless you can justify doing something more complicated. It turns out that the most efficient thing we can do is flip 1 spin. And I'll tell you why. And so let's just motivate that based on we're going to do the simplest thing possible. So our Monte Carlo move is we're going to choose 1 spin at random and flip it. Choose 1 spin at random, 1 spin at random to flip. Okay, that's going to be our Monte Carlo move. Okay, so we're all going to write Python, so now I'm going to write this in Python. Right, so what you're going to do is, to choose it at random, you need to pick a row at random, and you need to pick a column at random, and you can do that with Python's random integer function. Right, so you can do ix equals random, you could load numpy. Is this intrinsic? Do you have to load numpy? I load numpy in my code. We'll go over this. Has everyone used numpy? We'll go over the code. Okay, I think you might have to load numpy. But use this random integer function. Python indexing starts at 0. So if you give random int 0 to n, what it's going to choose is it's going to choose an integer that can be from 0, 1, 2, all the way up to n minus 1. Right? So you have n different integers which start at 0. And so you're going to do the same for iy equals random integer 0 n. So you can choose this at random. You know, back in the early days of Monte Carlo simulations, people were really worried about random number generators. Really worried, right? Because most random number generators are pseudo-random number generators. They're not purely random. And so people were really worried that using a pseudo-random number generator was going to give you unphysical. Now we don't really worry about it. We have so much experience that it doesn't matter too much if you're using a pseudo-random number generator. But if you read the literature, people were really concerned with that back in the day. Okay, so Python gives values. It can be 0 for ix, and it can be less than or equal to n minus 1. Right? So you get n. So your system is bounded 0, n minus 1. Okay, and so suppose we do this, and suppose that suppose we choose to spin 2, 3 at random. Okay, so let's choose 2, 3 at random. This one. Okay. So suppose we choose 2, 3. Okay, and I'm a little sloppy here because my Python index doesn't correspond to these indices. Okay, I'm gonna write everything in terms of starting at 1, but if you're in Python, you start at 0. Is that okay? I'm okay with that. Okay, so 2, 3 is gonna be this spin. We're back to indices starting at 1. So the next configuration is generated by attempting to flip this spin. Okay, so then what we do is we attempt. So the key point is we don't necessarily flip it, we attempt to flip spin. Okay, and the key point is the attempt. And so maybe I can just, let's just draw it out. And so just to be explicit here, right, we have our old system is this. I guess we have to draw it out again. Up, up, down, up, up, down, down, up, down, up, 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 down. Okay. 1, 2, 3, 1, 2, 3, etc. Okay, and my spin that I chose is this one. Okay, and so what I'm going to do is I'm going to attempt to move to this state, new state, where it's the same, up, down, up, up, down, down. This one's different, so now this one goes down, 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 up, 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 down. Okay, and so the key difference, 1, 2, 3, 1, 2, 3. Okay, so the key difference is we're attempting to do that. That's what we're attempting to do. Okay, straightforward so far. So now we're gonna define what we call an attempt probability matrix, right? Because we're gonna make this more formal. We're gonna put in a formal equation for decay of balance, and so we have to define matrices to do this. So an important quantity in Monte Carlo is the attempt probability matrix. Okay. And what this does And so what we're doing is we're breaking up our Monte Carlo move into attempting to do a move and then deciding whether we're actually going to do it. And that's not obvious why we're doing that right now, but it will be when we're done. Okay? So we're attempting, and then we're going to decide whether we're going to accept the move. Attempt, accept. Okay? Maybe I should put this here. We're going to attempt the move, and then we're going to accept the move. Okay? So this attempt probability matrix we can call alpha. And this is standard notation. If you read the literature, everyone uses alpha for attempt probability matrix. 2 underlines indicate a matrix. What this is it tells us the probability for generating a trial move between initial and final states of the system. So what it has formally has dimension number quantum states by number of quantum states. Formally. Right, so if we have a 20 by 20 2D Ising model, we have 10 to the 100 states. And so alpha is going to be 10 to the 100 by 10 to the 100. Okay. So this is going to be 10 to the 100 by 10 to the 100 for 2D Ising, or for 20 by 20 Ising. Well, no, sorry. 10 to the 100 isn't. 2 to the 400, sorry, is the exact number. Sorry. 2 to the 400 by 2 to the 400. I was just writing 10 to the 100 so we can see order of magnitude. Right. Okay. So you can't even, you can't buy a big enough hard drive to store this matrix. So it better be simple, otherwise you're not going to be able to work with it. And so the point is it's a very sparse matrix. And so whenever you have a huge matrix, everyone know what a sparse matrix is? Sparse matrix means you have a lot of zeros and only a few elements are non-zero. So it's sparse, okay? But it's sparse. It is very sparse. And what it is it gives the probability for generating a trial move between initial and final states. Okay? Gives probability of generating a trial move between initial and final quantum states. Okay? So that's why it has these dimensions, right? Because you have this dimension initial states, and you have this dimension final states, and each element of the matrix gives you the probability between going from one of these to one of these. Does that make sense? Yeah. So let's define it. So in our case, for us, and by us, based on this proposed Monte Carlo move, let's see what alpha is. So alpha, to define alpha, we need to define its elements. If it has dimension quantum state by quantum state, then each element is an initial quantum state, a final quantum state. So we use nu. So alpha nu, comma, nu prime, right, is an element of alpha, where this is the initial quantum state and this is the final quantum state. Does that make sense? Yeah? And so what is this? What is this element? Let's think about it. And so let's split it up. I told you it's very sparse. Why is it sparse? Well, it's sparse because my moves are only trying to flip one spin at a time. Right? So if this is my initial state, any state that differs from my initial state by more than one spin flip, I can't get there. Right? So alpha is going to be 0 if my initial state and final states are different by more than one spin flip. Does that make sense? So let's put that down first. So it's going to be something, it's going to be 0 if they differ by more than one spin flip. I'll write that down. And it's going to be something if they're connected by one spin flip. So what do you think alpha is for two states if the states are the same except only one spin is different? So alpha is the probability of generating a trial move between an initial and final quantum state. If two quantum states only differ by one spin, then I'm only going to generate the trial move if I pick the spin that they differ by. Yeah, 1 over n, where n's the number of spins, exactly. Here I'm using n, here n squared is the number of spins, so this would be 1 over n squared. Right. So alpha is 1 over n squared. Right? Because n squared is my number of spins. If I'm picking the spin at random, then 1 over n squared is the probability for picking that given spin. Right? So this is probability for randomly picking a spin. For random spin pick. Okay. So alpha is 1 over n squared if nu and nu prime are connected by one spin flip. Meaning if I make the right spin flip, I can make the states equal. So if and only if nu and nu prime are connected by one spin flip. Okay, and it's 0 otherwise. Okay? That make sense? Okay, so we're done with the first part of making a Monte Carlo. Now that's the first part. We attempt to make a move. We define a matrix alpha that tells us the probability for making a move between all the quantum states, all the different states of the system. Okay? Now we're going to talk about whether or not we actually do the move. Okay? So that's how we attempt a move. Now let's talk about how we decide whether or not to accept the move. And we have to be careful, we have to obey detailed bounds. Otherwise, we're going to get the wrong answer. Okay? Should we accept the move? Okay. So I'm going to tell you the condition for whether or not we accept the move. It's going to depend on the energy difference between the two states. Okay? So you're going to have to believe me for now. So let me write down the energy difference between the states because we're going to need that to decide whether or not we should accept. Okay, so I'm going to tell you this. Well, let me just write this down. After a Monte Carlo move is generated, or is attempted, after MC move is attempted, it is not necessarily accepted. It is not necessarily accepted. Sometimes we reject it. Sometimes we say that's a bad move. Okay? The probability depends on the energy difference between the states. Okay? The probability for accepting move depends on energy difference. Let me call it delta E between the initial and final states. Okay? So it depends on delta E. We'll see how it depends on delta E, but let's just calculate delta E. So delta E equals E final minus E initial. Let's calculate delta E for our move. Okay? Well, first of all, what is E? Okay? For 2D icing, E, remember, it's just all the interactions between neighbors. So E equals negative J sum over Ij prime Si Sj, right? Where the prime on the sum indicates you're only summing over nearest neighbors, right? So here's my system. I'm gonna flip this spin. When I'm calculating delta E, do I need to calculate all the interactions in my system? No, right? Because this spin is going to interact the same with its neighbors because its neighbors are the same, right? So when you calculate delta E, all the energy in the final state is going to cancel out all the energy in the initial state except for the energy of this spin interacting with its neighbors, right? So let's do that. So note we only have to compute, so only have to compute the energy of the flipped spin interacting with its neighbors. Okay, that's a key point. Because if you don't do that, and if you compute the total energy, your code's going to be extremely slow. Okay? And so this goes to John's point. This is why we don't flip all the spins at once. Right? Do you see that? Because if we flip all the spins at once, then we're going to have to compute the whole energy of the system. Right? If we, which scales as essentially order n, this is much easier to compute the energy for one spin. So that's why we've chosen to flip one spin.
Also, if we flipped all the spins, we'd be in the same.
Yeah, I was gonna say, it doesn't
That-
mean
that would
it makes
look-
all the
Right.
spins
Yeah, that would
really
make no sense at
Right,
all.
right. Or, I mean,
Exactly the same.
right. So all the spins isn't maybe a good example. Flipping like 20 spins.
Yeah.
Right. You would think that, okay, well, maybe we flipped 20 spins would be better. But 20 spins is 20 times the work here. So that's why you don't do it. Okay, so let's write down explicitly what delta E is. So you guys help me out. Let's write down delta E. I want E final minus initial, and I'm gonna ignore everything that's gonna cancel out. So what should I write here? I have delta E equals, let's write down E final, but only for the spin that, only for the part that's not going to cancel. So we need this guy interacting with this guy, this guy, this guy, and this guy, right? And this spin is 2, 3. So we need 2, 3 interacting with 2, 4, with 1, 3, with 2, 2, and with 3, 3. Right? So let's write that down explicitly.
So do our SIs and SJs, do those each have 2 indices?
Yeah, right. Because I switched notation.
Yeah.
This was my old notation. Sorry. And the reason I switched notation is because it's much easier to write this down when we're going through on paper. But when you're doing a computer code, it's much easier to label it by 2.
So our SI is going to stay fixed, and we're going to change our SJ to be each of these different positions.
Let's do it the other way around. Let's say SI is the spin we've chosen.
Okay.
Yep. So let's do it this way. Let's say so we have minus J, that's this. Okay. We don't know what this right now it's up. Let's just call it S23 initial. Let me note something else, right? So because I'm flipping it, S23, what notation am I using? Final equals minus S23 initial. Right? It's either 1 or negative 1, and so I'm flipping it, and so I just get the final spin equals negative the initial spin. So let's substitute that in here. So this should be S23 final, right? But I'm going to substitute minus S23 initial. So minus S23 initial. Everyone okay with that? And then we're going to add up all the interactions. So I told you we have the interaction with S22. Let's just go around the circle. S22, or I guess I'm not going in my notes. S24, S13, S33, right? So we have S22 plus S24 plus S13 plus S33. Right? And these spins are not changing. This is the only one that's changing. So that's the part I need to include in my final state, and then I have to subtract the initial state. So then I have to do minus, right? So all of this is the final part, right? So all of this is final. And then I have to minus the initial. The initial is a minus j, right? I still have minus j for my energy. S23 initial is the initial value of S23. S23 initial. Okay, and none of this changes because these spins have the same value. S22 plus S24 plus S13 plus S33. Okay, everyone okay with that? So of course this simplifies because the negative cancels the negative cancels the negative, and all of this just becomes 2j S23 initial times this other stuff. Okay, so I guess I'll go down here. Equals 2j S23 initial times S22 plus S24 plus S13 plus S33. Okay, that's my delta E. Everyone okay with that? So we know delta E. Now what we're going to do is we're going to define a acceptance probability matrix. So we defined a matrix, alpha matrix, for attempting a move between two states. Now we're going to define a matrix for actually accepting that move. Okay. So now define an acceptance probability matrix. Okay. For the probability of accepting a move, we're going to call this matrix, and this again is standard notation, ACC underscore underscore. So that's your acceptance matrix. So standard notation for this is alpha. Standard notation for this is ACC underscore underscore for acceptance matrix. Okay? And here's where detailed balance comes in. We don't know how to choose. We need to choose this acceptance matrix to satisfy the condition of detailed balance. So basically what I'm going to do is I'm going to tell you what the condition of detailed balance is, and then from that condition we can work out how to choose this. Okay. How to choose this matrix, and it must satisfy detailed balance. So if you're reading a paper and someone gives you this, and you don't know where they got it from detailed balance. And it must satisfy detailed balance. Okay. When I discuss detailed balance in Monte Carlo, I'm always tempted to discuss kinetics. I never know if I should or I should not. detailed balance is analogous to the principle of microscopic reversibility in kinetics. Does everyone, do people remember what the principle of microscopic reversibility in kinetics is? You can think of equilibrium as two ways. You can either think of equilibrium as being a thermodynamic phenomenon or a kinetic phenomenon. Right? Thermodynamic phenomenon says that your concentrations of your reactants and products must give you your equilibrium coefficient. Right? That's equilibrium. Or you could think about it kinetically. You could say the rate of reaction in the forward direction is equal and opposite to the rate of reaction in the backward direction. Right? So those are two equivalent ways of thinking about equilibrium. The second way gives you more microscopic insight, right? The second one allows you to write the rate constants in terms of the equilibrium coefficient, right? So maybe I should do this. I think it's important. Let me write an aside. Before we talk about detailed balance, it's really important to make the connection with kinetics. Aside. So kinetic equilibrium. Okay. So suppose you have the favorite reaction of physical chemists, A goes to B. Right? And of course at equilibrium, you have the equilibrium coefficient KEQ is the concentration of B at equilibrium over the concentration of A at equilibrium. And we have no stoichiometry coefficient, so our life is easier. Or you can say that there's a rate constant K and K minus 1 for the forward and reverse directions. And you can say also at equilibrium, it must be true that when A is at equilibrium, the concentration of A equals AEQ times the forward rate constant. This is the rate. The rate constant times the concentration is the overall rate of going forward, reactants to products. This must equal the rate of going backwards, which is K minus 1 B EQ. Okay, and this is called microscopic reversibility. Right? And it's the kinetic definition of equilibrium. It means the microscopic chemical reactions that go forward, the total amount must be equal and opposite to what goes backwards. Right? And of course, you can plug in your equilibrium constants for AEQ and BEQ and relate your forward and backward rate ratio to the equilibrium constant. Right? So that's how kinetics is related to thermodynamics. Everyone sound familiar now? Kind of? Okay, so to understand detailed balance, it's really helpful to think about the analogy with this. So detailed balance is just the analogy to microscopic reversibility in kinetics. So let me go over here so I have room. Detailed balance, they're essentially the same thing. I'm just going to say it's analog of kinetic microscopic reversibility. It's the analog if you think of your reaction as flow of probability. Okay? And if you can think of your reaction as a flow of probability, then you can write down the analog. And so that's what we're going to do. It's the analog if we think about flow of probability. Probability. Flow of probability is my chemical reaction. A chemical reaction is just flowing probability from reactants to products. Right? A mathematician would say that. A chemist would get angry. Okay, so let's try to write down the analogy. And try to motivate what the equation I'm going to write down. Right? To write down the amount of reactants going to the products, I need the amount I have, which is the concentration, and I need a rate constant for how fast I'm transforming the amount I have into the products. So the amount I have is going to correspond to the probability of the state. Okay. So the detailed balance is this. The condition is, okay, P nu, okay, the probability of state nu is your analog to your concentration of A. Everyone kind of see that, right? And then my rate, what's going to be the analog of my rate constant? This is where it gets slightly tricky. But you know I have two quantities left. I have alpha and you have accept. So those are both in the rate constant, right? Because to convert state nu from nu prime, I need to generate my move and I need to accept my move. So my rate constant is going to be alpha nu prime times ACC nu prime. Does that kind of make sense? So if P nu, I have alpha nu prime, ACC nu prime. And so this whole is like my rate constant. Like rate constant. And this is like concentration. Everyone sort of see that analogy? Yeah? So I follow what I have to do over there. I set the forward equal to the backward. And so the backward must just be P nu prime alpha nu prime nu ACC nu prime nu. Okay, and that's all my condition is. That's detailed balance. So I want to circle this, so I'm going to erase this so I can circle it. Right? This is it. Okay? That's the condition I must satisfy. So, I'm almost out of time. We'll have to finish this next time. From this equation, you derive what this is. We know what alpha is already. If we're going to be at equilibrium, then this probability has to correspond to the probability distribution of my ensemble. So we know what this is. We know what this is. We know what this is. We need to know these things, because we get these from this equation. So this condition defines elements of my accept matrix. Okay, and so that's what we'll work out next time. And so when you're generating a new Monte Carlo method and you're dreaming up these new moves, to finish your Monte Carlo method, you have to define two matrices, alpha and ACC. And so when you say, here's my method, you have to figure out what ACC is from this equation. And that's how you figure out your method. Okay? So we'll do that next time. We'll do that next time, and then I'll bring my computer, and we'll start looking at some computer stuff. Anyone use Google Colab? Maybe we'll use Google Colab. It's really cool, right? You don't even have to install Jupyter Notebook on your computer. You just Google Colab, and it gives you a free, basically Jupyter Notebook browser that runs on Google servers, and you can do whatever you want. So try it. Go home and try out Google Colab. It's a free computer. Basically, it's free servers. You can run any calculation you want on.
So it doesn't matter how crappy my computer is? Like, it's
Nope.
Nice.
That is nice.
I just wrote a proposal on this, actually. You know, when you write an NSF proposal, you need broader impact. And seriously, I said, look, Google Colab means that everyone has free access to supercomputers. Why is this not in the educational infrastructure?
That's fair.
So that was my proposal, is to take Google Colab and to make computing widely available.
That's good.
Thanks to Google, right?
Yeah.
Teach the youth.
Right after we
See you guys. Yeah, I was reading a lot of papers.
What?
After our discussion, I spent basically all day reading papers.
On the system.
Yeah, and let me turn this off.